Transitioning from a mid-level developer to a senior engineer requires shifting your focus from simply writing code to mastering high-level architectural design. This video breaks down the essential roadmap for building scalable, production-ready systems from the ground up, covering everything from API protocols to database selection. You will learn the core differences between REST, GraphQL, and gRPC, as well as the strategies for scaling through load balancing and robust security practices. Hayek developed this course.
Most developers cannot design systems or features from scratch. They can add to someone else's architecture with tasks with clear requirements and already on mature systems. But if you ask them to design something from the ground up, most of them usually will freeze. And actually that is the exact skill that separates mid-level developers from seniors, because seniors are also able to make decisions, design trade-offs, design the architecture from scratch, and make decisions with raw requirements. So companies are not paying six figures for people who can just code or follow instructions, but they are paying for architectural decisions, for making the system performant, for optimizing the data storage, and making the decisions that also affect the customers and the software that they are building. So in this video I'm going to teach you the exact concepts that I mastered to be able to design such systems from scratch and also get to senior roles. This is how I passed the system design interviews without any problems, and these are the skills that I learned to get to senior level within the second year of my career. So I'm not teaching you some theory from books or from newsletters. This is what actually works in real jobs and in real interviews. So let's jump into my computer to see what we are going to cover in this course. First of all, we will start from the foundations, the core concepts that you need to understand before anything else in system design. Then we'll get to API design, which is a big part of designing systems, like how to actually design APIs that scale and also make sense for other developers who will be using it. Then we'll get into databases, how to choose the right database for different scenarios and design your data layer properly. Next we'll get into caching, how to use caching, how to use CDNs, load balancing to make your systems fast and reliable. Then we'll get into big data processing, because that's a big topic in itself, how to handle large-scale data the right way. Then we'll get to designing for productions, like how to build systems that actually work in the real world, not just on your laptop or on a single machine. And lastly, you can see how I'm designing the systems for interviews and handling this step so that you can nail these interviews and get the offers that you need for getting to senior roles. Designing a system to support millions of users is challenging, but every complex system starts with something simple. That's why in this lesson we'll build a basic setup that supports just one single user, and then we'll gradually expand it as we go. Because starting small allows us to understand each core component before adding more complexity. So let's start with the first step and build a single server setup. Imagine that we're setting up a system for a small user base. This means that everything runs on one single server. The web application, the database, the cache, and also the other components. And this setup allows us to visualize the core workings without added complexity. Now let's break down how this single server setup handles the user requests. We have some users who are trying to access our website or our API on the server. They can be either using the web browser or a mobile app to access our server. And on the other hand, we have our server, which has the necessary files to serve to the web browsers and also the necessary API endpoints to serve to the mobile app. And it is hosted on this example IP address. Initially, our users don't have this IP address. They have the domain which they are trying to access. Let's say it's app.demo.com. So if they just type this domain name and hit enter, their web browser, for example, will contact the DNS, which stands for Domain Name System. This is a provider which maps the domains to the IP addresses. And in our case, let's say our domain name is mapped to the IP address, which is the server's IP address that we have. So now this DNS provider will send the IP address back to the web browser or to the mobile app, to our clients. And this IP address is our server's IP address. So now they have the location where they are trying to send requests. So with this IP address in hand, the user's device sends an HTTP request to our server asking for specific data, and then our server processes this request and sends back the requested data. This might be an HTML page for a browser or a JSON response for the app, depending on the request type. In this setup, traffic usually originates from two main sources. The first one is the web applications, and the second one is the mobile applications that are trying to access our server. For our web users, the server handles the business logic, data storage, and also presentation using HTML, CSS, and JavaScript. And for mobile users, communication typically happens over HTTP. These mobile apps request data from the server using API calls, and JSON is often used for responses because it's lightweight and easy for mobile devices to interpret. Here is an example API request that we can receive for our server. It can be a GET request to our domain /product/the ID of that product. And for this endpoint, we need to retrieve the details of a product. And here is an example response that we might send back to the client. This is a JSON response which contains the product ID. It contains the name of this product, some description, the price of the product, and some other metadata that is useful for the client. And then this will be used by the mobile app or by the web browser to display this product on the screen. And as we continue, our goal will be to identify areas where a single server might not be enough for the user demand. For now, this setup is ideal for small user bases, but it may struggle under heavy traffic. So next we'll explore ways to scale each part of the system to support more users effectively. Some key takeaways that we can have from this is that we need to start small. We need to begin with a straightforward single server setup to understand the essential components of system architecture. Now we also understand how these requests flow through your system, which is fundamental for building more scalable systems. And we also recognize the unique demands for web and mobile applications and how they interact with your server. And in the next lessons, we'll start looking at strategies for optimizing and scaling this setup. As our user base grows, a single server isn't enough to handle the increased demand, and to accommodate more users, we can separate our web tier, which is handling the web and mobile traffic, and the data tier, which is managing the database. This setup enables us to scale each server based on its specific load. But when it comes to choosing the right database, how do we know which specific database is the best for our specific application? When it comes to database selection, there are two main options. The first option is relational databases, or RDBMs, which are structured in tables and rows. Some popular examples are PostgreSQL, MySQL, Oracle Database, or SQLite. On the other hand, we have non-relational or NoSQL databases. These are suited for applications that require flexibility and fast access to large volumes of unstructured data. Some examples are Cassandra, MongoDB, Redis, or Neo4j. Let's start by exploring the relational databases. These databases use structured query language or SQL for finding and manipulating data. The data here is structured in tables, which are the fundamental building blocks of SQL databases, and these are similar to spreadsheets. Each table consists of columns, which can be thought as the fields or attributes of the table, and it also consists of rows, which are single records within this table. For example, if you imagine a customers table, within this table we can have columns like ID, name, age, and email. And for each rows, we can have specific customers like the ID of 123 and the name will be John and the age will be 30 and so on. But what are the advantages of using an SQL database? First of all, they support complex join operations across multiple tables. For example, if you imagine we have a customers table and also a products table, and now we want to create a separate table that will connect the customers and the products that they have ordered. With SQL, you can join these two tables together into an orders table, and this will hold the information about the customer IDs who have this order and also the product IDs which this customer has ordered. And this process of combining two or more tables into one table are called join operations in SQL. And the other big advantage is they provide robust data consistency and integrity, especially for transactions. Transactions in SQL are a sequence of one or more SQL operations that are performed as a single atomic unit, and each transaction in SQL follows the ACID acronym. You can think of a transaction example like a bank transfer. So first of all of the transactions are atomic, which means that the entire transaction is treated as a single unit, which either completely succeeds or completely fails. Each transaction is also consistent, which means that it transfers the database from one valid state to another valid state. And they also come with isolation, which means that modifications made by concurrent transactions are isolated from one another and they don't interfere with each other. And lastly, they come with durability, which means even if the system fails or the database server fails, the data will still remain there. And now let's have a look at non-relational databases. Non-relational databases can be in different forms. For example, we have document stores like MongoDB, or you can use wide column stores like Cassandra, key value stores like Redis, and graph stores like Neo4j. Let's have a look at each of these types separately, and let's start with the document stores. MongoDB is the most popular example of a document store, and the data here is stored in JSON-like documents, which allows us to have complex data structures within a single record. Next, we have wide column stores, where data is stored in tables, rows, and dynamic columns. Some examples here are Cassandra or Cosmos DB. The main advantage of these databases is they can handle massive scales and are very good for many write operations. The other option is graph databases, which focus on storing the entities and their relationships as graphs. An example of a graph database is Neo4j. For example, in Amazon, they use the Neptune graph database, which helps them to make you product recommendations based on your previous orders. And the other popular type is key value stores. Here, data is stored in key value pairs. The biggest advantage of key value stores is their simplicity and speed. Since they are primarily stored in RAM, reading and writing to these databases is extremely fast compared to other databases. Some examples of key value stores are Memcache or Redis. So that's the main four types of NoSQL databases. Now let's have a look at the advantages of these NoSQL databases. If you have a look at the same example that we had for the SQL databases, where we have customers and products and we want to join them in orders. For example, in MongoDB, you could have this as a single document, so you could store all of the user data, also the orders and products in a single document. And because of this structure, the NoSQL databases can handle highly dynamic and large data sets without the structure imposed by relational databases. And also, they are optimized for low latency and scalability. So when should you use relational versus non-relational databases? Here is a quick comparison of both. If your application data is well structured with clear relationships, then you should use SQL databases. For example, if you have an e-commerce application tracking customers and orders, that's a good use case of using an SQL database. Next, if you need strong consistency and transactional integrity, for example, if you have a financial application or banking system, then you should use the SQL databases. However, if your app demands super low latency for quick responses, then you should go with non-relational databases. Or if the data is unstructured or semi-structured, like JSON objects, and the relationships aren't that crucial, then you should also go with NoSQL databases. And lastly, if your application requires flexible and scalable storage for massive data volumes, for example, a recommendation engine storing user activity data and key value format, then you should also go with NoSQL databases. Let's explore the two primary approaches to scaling, which are vertical and horizontal ways of scaling. And we'll also see why horizontal scaling is generally more suitable for high traffic applications. First, we have the vertical scaling, or sometimes it's also called scale up. This just means that we are adding more resources to our existing server, meaning RAM, CPU, or any other resources that might help us to handle more traffic. And this approach is simple and works well for applications that have low or moderate traffic. However, it comes with its limitations, which are firstly resource limits. There is a hard cap on how much you can add to a single server. And eventually you will reach a limit on how much you can upgrade your new server. And the second reason is lack of redundancy, meaning if this server goes down, you don't have any other servers to serve your users, which means that your whole application goes down with your single server. On the other hand, we have horizontal scaling, which is